Good morning, good evening, everyone. Thanks for joining us today for our webinar on the impact of EMCCDs on speckle imaging. Today we have Nick Scott and Steve Howell from NASA AMA's Research Centre, and we have Andor's astronomy specialist, Ines Yuvan-Bolea. Ines also today will have a special surprise announcement just before the Q&A. If anybody has any questions that arise at any time, please just put them into the chat box, and we will answer these at the end of the presentation. And if you also have any questions after the webinar, you can always certainly email us, and we will respond by email. So I'm just going to hand over to Nick, who's going to start today.
Okay. All right. Thanks, Sean, and thanks, Inez, for inviting me, and thanks, Steve, for joining in as well. So yeah, I want to talk about, we've got 3 instruments we've built in the past few years that use 2 of the Andor EMCCDs, and these were built specifically for doing speckle imaging. So I can share a little bit with what we've been working on with those. The background image you have here is actually an artist conception by Joy Pollard, Gemini, of Kepler 13AB, which is one of the first I can talk about. It got a lot of press into last year for it's home to an exoplanet, and it was uncertain which star of the binary pair that the exoplanet was hosting the exoplanet. And what we did, it worked out as a great test case for speckle compared to aperture photometry, because it was the binary separated by 1 arcsecond. So it's one of the cases where we can do both traditional aperture photometry and do speckle interferometry and compare the results. And so we did that in the 2 colors and imaged the transit of the exoplanet. Actually, Steve did that, and we did the observations, and we were able to confirm that with LPK, which is our speckle instrument at Gemini North, that the highly irradiated gas giant Kepler 13b orbits Kepler 13a. So to talk a little bit about what speckle is and why we care about these fuzzy blobs. If you have a single star, and here this big circle represents the turbulence of the atmosphere, like the coherent cell, or isopynactic patch is another name for it. You see the star as a bunch of speckles as the atmosphere is changing. It's very analogous to being at the bottom of a swimming pool and trying to recognize faces looking back up from underwater. If you have poorer seeing, so you've got small patches of seeing cells, then you get many speckles. If the star is actually a binary and they're close enough, then you can get an interference pattern or interference occurring within the atmosphere. And then you get these correlated speckles. So both the position angle and the separation of the speckles can be traced back to the position angle and separation of the binary you're observing. So Kepler 13AB falls in between this regime of having a well-separated binary and a close binary, and where you get correlation between the speckles, and you can still see there's a centroid for each star. What our data looks like is along the top here, the first blue frame on the left is each frame coming in. So it's fuzzy blob moving around. The next frame over is showing those frames being stacked, and this is what you would get if you were doing a longer integration as opposed to many short integrations, and you end up with a point spread function or an area pattern. If we take the Fourier modulus, you get this pattern, this interference pattern, and by doing some image reconstruction, you end up with the image on the far right, which is the binary pair. And the separation of the binary and the position angle is revealed in the Fourier pattern. So going from the left to the right, we go from this raw 1,000 speckle frames and end up with a really nice diffraction limited image of the binary. And then the bottom just shows same thing, a movie on the left, and then the corresponding reconstruction on the right. So why do we care about speckle, and why is it important now? It's really come to popularity with Kepler K2 and now TESS, because these surveys are trying to find as many transits as possible. They're looking at large sections of the sky. They have very large pixels. And in the movie in the top here, you see that's one of the stars from Kepler. And these huge, each pixel is 4 arcseconds. So if you're trying to find the transit, you really don't know if it's a single star or a binary, and that can mask your exoplanet signal or mimic the eclipsing binary could mimic an exoplanet signal. So to be sure of what you're seeing, this kind of reiterates that in a more astronomer-friendly way. TESS is going to have, or has 20 arcsecond pixels. Kepler has 4 arcsecond pixels compared to the Seeing Limited. And you can do Speckle, and what was just a complete pixelated blob becomes 2 separate stars. And then there's a direct relationship between the observed transit and the radius of the exoplanet. So if you have a binary and you detect an exoplanet, then your exoplanet may be much larger than you think it is, or it might be a star mimicking it. And obviously many stars are multiples, so about 33% are double, 8% are triple, and 4% are more than triples. And 40 to 50% of Kepler K2 TESS objects may have companions, and this biases both your occurrence rate for the types of planets you're trying to detect, and it makes you underestimate planets' radii by 50 to 60%. Just do a quick review of like what we mean by speckle, as opposed to like lucky imaging or some of the other techniques for high angular resolution. It's all about limiting the atmosphere. So there's a few ways to do that. One is like adaptive optics or other techniques, but the one that Speckle utilizes is interferometry. So by looking at the interference pattern between the stars, you can recover the original perfect pristine data before it interacted with their atmosphere. And you can measure, with proper long baseline interferometry, you can measure diameter of stars, like Betelgeuse was measured in 1920. This technique was discussed by Lebray in 1970 of, if you, even with photographic plates, if you had a very bright star and you take a very fast exposure, you get this speckle pattern that appears. Unfortunately, because of signal to noise issues, you have to take a long exposure, which blurs the speckles, and then we end up with an area pattern. So if we had a way to detect, it's a sensitive enough detector that could run fast enough, then you can freeze these speckles and reconstruct your diffraction limited image exactly as if there was the telescope was in space. The original Lebray paper it's really brief. It's like 3 pages, mostly these images. And it was just kind of if you could do this, this would be great, and a couple examples. And then it kind of sat for a while. One drawback to the Lebray technique is that it was just looking at the Fourier modulus, so you could only produce center-symmetric images, so there's ambiguity in direction. In '74, Knox and Thompson introduced the cross spectrum, which is a second-order correlation in Fourier space. And that basically was let you get phase information of the object. And when you put the phase with the modulus, then you're getting a true diffraction limited image. And so we could produce the first like unambiguous reconstruction of arbitrary straight shapes instead of just center-symmetric. Why do we care about the phase? I can illustrate this really easily with a dog and a cat. That most of the information of the image is carried in the phase, and that you need this phase as well as the intensity to produce a solution for the reconstruction. So the technique that our instruments work on was a pipeline developed by Elliot Horch. It was built off of Weigelt and Lohmann's work, which is speckle masking, what's called triple correlation theory, or bispectral analysis. So this is a third order correlation in Fourier space. And basically you record the PSF of a comparison object. So you get and we still do this now, we observe a calibrator star for the PSF, and then we look at our science star, and you can produce a synthetic reference star by shifting the speckle pattern around. And that way you preserve the phase, and you can produce these images. So this gives a higher signal noise, and it has less systematic errors than some of the previous techniques. So this is the background of how our instruments work. And this is what our data looks like. Top half of the page is one binary pair, bottom half, 8 images, is another pair. So I have a close binary and a wide binary. So the top left black and white frame is just a representative speckle frame. So it looks like a cloud of blobs. And then we have some of our Fourier reconstructions, and then the bottom corner is the actual reconstructed image. And little dot on there is the Raleigh criterion for the area pattern, so the diffraction pattern we're getting. So our resolution compared to 1 arcsecond spacing. So this is an easily resolvable binary. Notice that it's the fringe spacing, tight small fringes is a wider binary, big fringes is a close binary pair. And then you just measure the angle to get the position angle for the pair. So this is most of what our data analysis comes out with. And one of the nice advantages to this technique is it is incredibly fast. So this is a fairly bright binary, I think around 5th magnitude. 1 second of data, and you can already see the image coming in. Oh, we have by the way, the reason there's 2 colors is we operate 2 cameras at once, one in a red channel, one in the blue, both in the optical. So we have a blue channel colored in green here and a red in red. The 1 second, you can already see the binary coming in. We typically do, for a bright star, we take 1 or 2 sets of 1,000 frames at 60 milliseconds each for the Gemini telescopes and 40 milliseconds for the WIN telescope. And you see if we go to 20 minutes of observations, the fringes, the contrast gets deeper in the fringes, but there's really not a significant change between 40 seconds and 20 minutes in the data we get on the binary itself. So our instruments are able to run extremely fast, typically getting through 50 to 100 targets in a night of observing. And this is the contrast curve we come up with. So this is separation of the binary pair compared to the delta magnitude. And our instruments are NESI, Alapeke, and now Zorro. So these different curves show the contrast curve. And the boxes in here represent long baseline interferometry, which fills in the gap where we lose resolution at the diffraction limit. And there's also a comparison for like RoboAO that can do long separations as well. So to compare this to adaptive optics, so the dashed lines here are different. There's Keck and GPi. They can obviously go much, much fainter than we can. However, because they're further in the infrared, they're not able to get as high a resolution in the close separation. Also, each of these observations requires a laser for the AO and will take 40 minutes or so for an observation, whereas we're much more efficient in how many targets we can get to. So it's really a complementary technique. And this is just a zoom in of where we hit the diffraction limit and where long baseline interferometers like Chara can fill in the extremely close binaries and actually resolve the stars in the pair itself. One of the common things you'll hear if you ever talking about Speckle imaging is, oh yeah, we did that, that's lucky imaging. Lucky imaging is different. It's similar in that you need a lot of images recorded fairly fast. However, those are not combined in Fourier space. You're just doing image shift and add. And that does get you an improvement over the native seeing, but it usually requires throwing away 90% of your frames effectively. So it doesn't get the same efficiency. Whereas we don't throw away any of our frames. If we take a minute of data of 1,000 frames, we use all 1,000 frames in our reconstruction. So we are able to actually get the diffraction limit and maintain that efficiency. So the reason this has been enabled since Lebré is moving away from moving and changing technology in the detectors. So first, after CCDs, ICCDs, the intensified CCDs came out. However, the problem with them is they had a low resolution and low quantum efficiency because they were mostly interline detectors. So every other line was recording the data, so that didn't really help Speckle much. But EMCCDs, what we've used, basically have a high voltage electron multiplying register at the end of an effectively normal CCD. And this allows you to get much higher signal to noise and run 10 to 100 times faster than a CCD, and with a high quantum efficiency. Tokavinen published the first Speckle imaging results with EMCCs in 2008, and he's been doing it ever since. The next technology, to really be implemented would be EMCCDs. So taking a CMOS detector, where you're reading directly off each pixel and have the electron multiplication on the back of each pixel. And the first results for this were reported in 2015. Our current technology we use are the and/or EMCCDs. So I tried to compile a list of all the instruments that are doing Speckle, and I can sort this out a little. So I tried to look up everything using EMCCDs. Okay. Try to use list everything using EMCCDs. However, a lot of these are infrared Speckle, which is a different technique, or Lucky imaging. And what we're left with are, I want to see what telescopes have Speckle instruments at all. So there's our group at the top in blue here, which started with Dizzy. And Dizzy was a portable instrument that was able to be moved between WIN, Gemini North, and Gemini South, and it's now at the DCT. Coming after Dizzy, we built Nessie for the WIN telescope, which is dedicated and stays on WIN, and Alapeke for Gemini North, and Zorro for Gemini South. They're all sort of very similar instruments in how they operate and how the data reduction is done. And then there's also USNO has, they're working on an EMCCD instrument as well. And so if you take every telescope over 2 meters in the world, these are the ones that have some sort of Speckle instrument currently on them that I can find. I may have missed, if I missed one, someone please tell me. So this is what our instruments look like. The original one is Dizzy on the left. It was then replaced at WIN by Nessie in the bottom. And you can see it's a fairly very simple design. It's basically an optical bench in a box with as much off-the-shelf components as possible. So we went with the Andor cameras, Zaber stages to switch between a narrow field of view and a wide field of view, which is something additional to the new instruments that Dizzy couldn't do, and 2 filter wheels that are just off the shelf from Newport, and an input lens. And on the right is the design for Alapeke and Zorro for Gemini North and Gemini South. This instrument had to be more complicated in that the instrument port we could attach to was in use. So we built a pick-off mirror that could be swing down and be inserted into the beam and redirect it to us. So effectively made a new instrument port for Gemini North and Gemini South. And we fit between the instrument mounting surface and GCal. And there's a photo of it in there. It's a tiny instrument. It's the size of basically a profile of a laptop, but 11 inches tall. And then the camera's hanging off of it. Here's our group. This is the Speckle imaging group at one of our last meetings where we're all together. Don't know when we'll get to do that again, but hopefully at some point, at least virtually. And then the install at Gemini. So there's Steve, myself, Rachel Matson, and Emmett Quigley, who's at NASA Ames. So the instrument itself went from the typical napkin sketch into something more complicated. So the pickoff mirror is in the center, redirects light to the right in this image, goes through an input stage, 1 of 2, either the wide field or the Speckle mode, hits a dichroic at, I think it's at around 680 nanometer to split off the blue, and the red passes through, goes through a filter wheel where we have Sloan filters and narrowband filters for Speckle. The narrower the bandwidth we use with interferometry, the better you can measure retain your fringe pattern. So narrow bandwidth is gonna help you with your reconstruction. And then the camera's at the end. It all fits on a cart, which is not something you could say for many instruments. It was kind of amusing. Basically roll it up and bolt it on. And here's where it is installed with a plate covering where the Andor camera, the red camera goes, and the blue one hangs off the bottom. So there's Steve, Rachel, and I at Gemini with some of the assembly. You see from the bottom right picture, it's a very compact instrument, but very productive. I think everyone of this, if it wasn't clear in where everything is, there's motion control for the pickoff mirror, motion for the 3 stages that can select our lenses, and then the cameras. And it's really just a 2-lens optical setup, so it could not be simpler. So we use dual and/or Xi and Ultra 888s. And we typically bin down, or not bin, but use silicon ROI of 256 by 256 and do 1,000 frames at 60 milliseconds. We get a pixel noise of about 150 electrons, and we're sensitive to about 5.5 electrons per 80. There's the field of view in wide field mode is about an arc minute at the Gemini telescopes and an arc minute at WIN. And then the only difference between the Geminis versus the WIN, other than the telescope diameter, is that the Speckle field of view at with NESI is about 20 arc seconds, whereas it's about 7 for Alipeke and Zorro. So we get about 10 millarc seconds per pixel. We do have a U filter, so if we have a very bright object and we can use U, we can get a maximum resolution of 11 millarc seconds. 25 is about more typical. A little bit on the EMCCDs. These are some of the tests we performed on it. We get about 100, 200 electrons of read noise. At the high EM gain settings, it drops to 1 electron. One of the issues, especially with the early EMCCDs, was clock-induced charge, which creates spurious counts in pixel by pixel. We minimize that by always using the fastest readout rates possible and shifting the rows as fast as possible. And so that puts the clock-induced charge from 6% down to 0.05%, which makes it negligible for us. The diagram, the plots here are just some of the, where we're linear in the different range. So the top plot is a constant light source, 2 different values of ND, and then stepping up through the gains and seeing just where we can go with the gain and stay in the linear regime. There's a photon transfer curve on the bottom if anyone's interested, and then where we are in linear versus non-linear for a maximum amount of ADUs depending on our gains. So we basically keep within this parameter space and we can observe whatever we like. This is a noisy plot, but this is all the filters we have. The narrow ones are the blue, green, red, and yellow, and then the Sloan ones fill in. So if we can do all the things you can do with the normal CCD, aperture photometry, all of that in any of these filters, and then we can switch to Speckle and get the diffraction limited images in filters at 466, 562, 716, and 832 nanometer. So to control all this, we wrote our own software and/or provided a nice Linux API, and we were able to basically make 3 servers, 1 for each camera, and then what lords over all of those, and they basically share memory with DS9 windows. So we can get this kind of Speckle GUI and run the 2 cameras simultaneously and keep them relatively synced up and still talk to the telescope. So it makes operation pretty simple. So on to the science we've done. I compiled all the science programs we've had. It's all through NOAO since 2016A to 2019B. There's 58 total proposals, about 140 nights, divided up between at WIN, NESI, and earlier ones were DISI at WIN. So NESI has now taken over the DISI at WIN slice of this pie. Alipeke was fairly new, and Zorro is the newest. So their numbers will grow, and DISI at Gemini South is gone and will be taken up by Zorro. So effectively, I'd expect going forward this look like a third between each of 3 instruments. For 2020, we've got roughly 100 nights a year. We're averaging about 100 nights a year at Gemini and 20 nights a year at WIN. 20A has 17 proposals asking for over 400 hours of total time at Gemini. Of course, not all of that's going to be gotten, but that's how much is being asked for. So we're at a healthy 2 to 3 to 1 subscription rate. Some of the proposals, the most of our work is the exoplanet. That's under Steve's program, and he can talk some about that if he wants. And that's all going for figuring out binarity and double stars around potential exoplanet hosts. But we also get proposals that are novel. So that's almost 3/4 of our stuff. But a lot of the rest is stellar astrophysics and some other things like imaged solar system objects, near Earth asteroid diameters, A lot of questions of multiplicity of nearby K and M dwarfs, because we can go fairly faint in the red. Imaging brown dwarfs. Looking at long-term radial velocity trends, determined binarity of radial velocity planet hosts. I won't read all of these, but interacting binary systems and Wolf Rayet stars, jets, and outflows are one of the other things we're starting to look at. So we're open to any proposal, not just exoplanets. Some of the recent papers that have been made with incorporated these instrument results. This one by Elise Fallon was optical and near-infrared imaging of host stars of Kepler objects of interest. Looked at about 90% of the confirmed and candidate exoplanet hosts, found separations, position angles, and delta magnitudes for all bound and line of sight companion stars. So ended up with about 10% of observed stars with one or more companions within an arc second, and 30% had a companion within 4 arc seconds. So this will shift the number of KOI planets with radii smaller than 2 Earth by 2 to 23%. So it's changing the occurrence rate and changing the radii. So it's kind of a theme. The density of planets in multiple stellar systems, also by Elise and Steve, takes that previous result and applies it to planets with known masses and radii, and analyzes the effects of close companion on the planetary bulk density. So I looked at 50 planets orbiting 26 stars in the Kepler field, and what happens with the transit dilution means the planet radii goes up and the planet density goes down. So if there's a faint companion star, the density may decrease by a factor of 3. So on the right here, this plot shows different models of composition for the just bulk density of these exoplanets. And this mass versus radius plot, if you take that, and on the left here are those points as detected, and on the left here is if you assume the planets orbit the primary star of the pair. However, on the right, if the planet orbits the secondary, then all the bulk density goes up on this plot, which is toward, instead of being Earths, goes into super Earths or giants. Johanna Teskey looked at about half arc second companions of Kepler and K2 planet hosts and their exoplanet radius distribution. So looking at like the Fulton gap, she found the Fulton gap is robust, even if there's undetected stellar companions, but the gap became broader and shallower, and it can shift. So let's see if I can show that. Yeah, so it shifted from 1.8 to 2.2 Earth radii, which means an increased water or ice versus pure silicon rock. So it's shifting from super Earths toward mini Neptunes. So it's basically driving home the point that you have to account for binarity when looking at exoplanet distribution. In 2017, Leah Hirsch looked at 170 KOIs within 2 arc seconds with AO, Speckle, Lucky, or HST imaging. And she found 80% of companions were less than an arc second apart, and 90% of companions less than a half arc second were bound. And she found that if you assume it's equally likely that the planet's orbiting the primary or secondary, that unless you go back and vet these candidates, nearly half of all Kepler planets only have radii underestimated by 65%. Steve and et al. Looked at TRAPPIST with Dizzy at Gemini South, and this provided the highest resolution images at the time for TRAPPIST, 27 milliarc seconds, an image from about a third of an AU to almost 15 AU out. And this work excluded all possible stellar and brown dwarf companions, so proving that TRAPPIST-1 is a single star. And this is the completion of that, the detection percentage versus projected angular separation. So this basically rules out any companion earlier than a T7, up to 8 AU. So this helps confirm that the TRAPPIST and very interesting planetary system is real. Rachel Matson more recently looked at companions, found that most companions within 1 arc second are bound, while only about 50% within 2 arc seconds are bound. So the plot on the right here with the circles is our contrast curve, This is all K2 binaries. And the open circles are bound. This is all simulated, but the open circles are bound. The black filled circles are line of sight. So you see there's just this turnover point, and the numbers at the top represent the bins for whether there's 99% of them are bound versus 87, 59, 34. So as you go further out, as you'd expect, your line of sight takes over from your bound companions. And the question with this is that if it is a binary, does it play some role in suppressing planet formation? Or you're equally likely to get a planet to form, whether that's a binary or a single star. That's what the bottom left plot is trying to determine. It still needs a lot more data to see which curve it fits, whether it fits the solid line here from Krauss or the dotted. But as we get these filled in, we hope to see. And finally on this, Rachel, Steve, and David Ciardi looked at what companions could be observed. So each one of these lines represents whatever star you pick on the line. You see the dashed lines that are vertical show that with which instrument you can detect all the planets to the, or all the companions to the left. And then, so basically for the top curve here, if you go to the first red star, you can detect every star earlier than that with Alipeke, with Nesse, and with the gray lines represent the contrast ratios at which the planet radii will have correction factors of either 1% or 0.1%. So this is basically, if it is a companion, how much it could affect the radius. More recently, actually just this week, we've been working on doing time series photometry. So we can not just do Speckle, we can produce light curves. And we looked at a binary white dwarf system. Took 320 frames. This is data from earlier this year, but we've been analyzing the light curve. And we're able to get sub-second precision in the time series of this this eclipse. I think I can make this play. Don't need sound. Yeah, so it can make this is our light curve. So we've been working on this now. So time series photometry is something these EMCCDs can enable with our instrument at a rate that I don't think has been explored very much. Some of the future instruments that are planning on using EMCCDs, Gerard Van Bell is working on Quizy, which I unfortunately was, I believe, ready to go on the telescope the day before quarantine started. So it is now sitting, and it was almost installed on the telescope. It's a 4-channel near infrared and optical, so builds off of DISI. It's at the DCT, and then he has channels for potentially wavefront sensing and infrared detectors. Let's talk really briefly about looking at asteroid Cleopatra. So we can resolve images as well and try and get shapes on some of these near-Earth asteroids, as well as reduce uncertainties on the radii measurements. So we've done this with Cleopatra and also with Phaethon. So we've looked at Phaethon, found a diameter about 6 kilometers. So it's interesting if we get any near-Earth asteroids that are bright enough that we can observe, we can try and get resolve their peanut shape or if they're spherical. Extended objects are another option. We're working with Elliot Horch on adapting the Speckle techniques to work on extended objects. So the top left here, the seeing limited image from WIN with Nessi's, this is a 3.5 meter, and then reconstructed to get let's see, about 4 times better than the native seeing. This was done in about 3/4 to an arcsecond seeing, and then our reconstructed image comes up with a 1/4 arcsecond, and that's just from 500 frames of imaging. Similarly with Jupiter, we've got about a consistent 3 to 4 times improvement over native seeing by using a speckle reduction on the extended object. So we get this middle image in the reconstruction compared to like the HST image. This is excellent for things like tracking storms or dark spots. So we've got a program to look at Neptune and try and image any spots on it and track them to help supplement space-based imaging. And we can also, because we have this wide field optics where we can observe an arc minute at a time, we can do speckle in this wide field mode and kind of make a mosaic of speckle of diffraction limited images and use that for astrometry of clusters. So still working on this, but we're able to get astrometry residuals in the like 5 milliarc second range and 0.05 mag accuracy on aperture photometry. So we could do an entire cluster in a few shots and do speckle reductions. One of the things our instruments have been used for is to help support SOFIA. So SOFIA was going to observe a occultation for the TNO Varda, and SOFIA is obviously very difficult, very expensive to fly, and it's a fairly risky in that they have to have their path mapped out perfectly to observe this occultation. So what we're able to do is vet their target, the object that was lighting up the occultation is a single star and not a double, because that would change the path of the shadow and could result in many miles off course in their flight plan. So that was an easy thing to do that helped save SOFIA a lot of money. And next, what we're working on, we've just installed at Gemini South an H-alpha filter. One of the plans is to observe the jets of Wolf-Rayet stars in H-alpha and compare them to continuum in the SDSS. And then I'm working on adding in low dispersion grisms for things like high Z transients, GRBs, or exoplanet host flares. Just trying to leverage, taking advantage of the sensitivity of the EMCCDs and the large aperture of Gemini. So all of these instruments are open to the community through the NAO proposal process. Nessie is WIN at Kit Peak, Alapeke is at Gemini North, Zora at Gemini South, and we're transitioning from block Q visitor instrument operation. So it's sort of facility instruments. We're not facility instruments, but we're now what's called resident instruments. We're always on the telescope, so targets opportunity are available, and the staff there is being trained up on how to use them, and with remote support from us. So it makes it a very quick turnaround to do any TOOs. All right, so just to summarize, there's a crash course in speckle interferometry and why we care about high resolution imaging in regards to exoplanets and stellar research, and why EMCCDs have revitalized this speckle technique, the sensitivity and the speed at which they can run, and some of our projects and what the rest of the community is doing. And kind of the takeaway is that the small space telescopes like TESS and Gaia perform relatively poorly at high contrast because it's not what they're optimized for. But speckle is a great technique from the ground to do this follow-up and vetting. And it's an extremely cost-effective means to get the diffraction limit with a single aperture. So our instruments are on the order of 200K, and a lot of that is the indoor cameras themselves are the expensive component, and the rest is just built to support them. And with that, I'll hand off to Inez.
Thank you very much, Nick. That was extremely interesting. If we just want to go over to Enos now.
So Inez, I think you should have it.
Sorry?
I think you have it now.
Yes, I just have to select the correct screen. Yes, I think this is working now. Just let me know when you see it.
Yep.
Yeah?
Yep.
Okay, perfect. Good then. Thank you so much, Sean, at first for the introduction, and then thank you, Nick and Steve, for this great presentation. It was really, really interesting to hear about your project and all the different results. So my presentation now will be fairly short, but I just want to give you a brief overview of our indoor cameras for high-speed astronomical imaging. So I will start off the presentation with giving you an overview of our cameras for astronomy in general, but then, because this is about high-speed imaging, I will focus on our EXON EMCCDs and our SCMOS portfolio. And I will also mention some examples of projects which are already using our detectors. So like I said, I want to start with the broad overview of our camera portfolio. You see here, we have to offer some large area and high resolution CCDs. That is called the ICON series. And what is good about this camera is that we really have different options between 1K to 1K up to 6K by 6K sensor size. Then those cameras are really sensitive because we have back illuminated sensors, and also some are available with deep depletion. And also we have really a low cooling on these cameras, which you can see here. So it cools down to -100 degrees Celsius, and also you read out quite slowly. So you really have low noise properties. And I would always recommend these cameras if you observe between, so if your exposure time is between seconds up to an hour or a bit longer. And so those were our CCD cameras, but like I said, this presentation should be to focus on our cameras for high time resolution astronomy. So our EMCCDs, where you already heard a bit about them, but basically we have two different options, and I will talk, I'll give you more details about them in a bit. And then we also have our SCMOS portfolio, where we have different front and back illuminated camera versions, also with different sensor sizes. So that is just to give you a brief overview of what we have in general. And now I'd like to focus on EXON Ultra EMCCD. So I know you heard a bit about them already, but what does EM actually mean? So EM stands for electron multiplying, and that just means that the sensor has an on-chip amplification. So the signal that you take is amplified well above the read noise floor before you read it out. And that happens even if you image at high speeds. And because of that, the camera is also really sensitive and works really well in low light conditions. And also it is really sensitive because we're again utilizing back illuminated sensors. Another good thing about this camera is that we don't have a mechanical shutter. So it is based on frame transfer structure. And you can see that here on the right-hand side, you have the light falling on the image section. Then we have the other area which stores the image, and then the signal will be amplified and read out. So that is the basic principle of how an EMCCD works. And as I mentioned in the beginning, we have two different options. So it's the EXON Ultra 888 and 897. But the basic differences are actually just the sensor size, as you can see here, then the pixel size. Then the 897 has a bit of a higher pixel well depth. And because of the smaller size of the 897, you can also achieve higher frame rates at full frame. And also if you just decide to crop the image, so you choose a smaller region of interest, for example, you can go a bit faster. The camera is also cooled to very low temperatures. And like you can see here, with the back illuminated sensor, you can reach up to 95% quantum efficiency. And another thing that I really like about this camera is that you don't have to use the EM gain. So you can use the camera as a standard CCD as well. So it's a really versatile camera solution. Good, so I told you a bit about the characteristics of EMCCDs, and I would just like to tell you where these cameras are used. So you heard about its use in Speckle imaging by Nick. But also we have the use in Lucky imaging. So as an example, I give you here the two-color instrument, which is based at the Danish 1.54 meter telescope in La Silla. You can see the instrument set up here on the right-hand side. So this is basically just this little box, and you have the two endo cameras here. And this is the whole setup of the telescope. You only see a fraction of it. But also, if you're interested in more details, you can look up this article. And what I also really like about this Lucky Imaging project is that they could produce a number of different scientific discoveries. So they detected exoplanets through microlensing, or they discovered variable stars and dense globular clusters, and they even discovered 2 rings around an asteroid-like object. So I really like the fact that with EMCCDs, you can really cover all kinds of different science goals, which was also mentioned in Nick's presentation. Then the IXONs are actually also used, for example, as guiding and science cameras for SOFIA. So that is the Stratospheric Observatory for Infrared Astronomy. It's really a flying observatory which carries a 2.7 meter reflecting telescope. And like you can see here on the right-hand side, this is just the setup of the telescope. And it shows you that here we have 2 different areas. So on the left-hand side, there's the cabin side. And on the right-hand side, there's the cavity side. And we have different temperature and pressure conditions. And if you look a bit closer, you see here the focal plane images. So we have an Andor IXON Ultra as the FPI here on the cabin side. And then even we have 2, I have to say, heavily customized IXON Ultras on the cavity side, which are here as the fine field imager and the wide field imager. So, but that is possible too. We do offer our cameras as well in a customized version. Okay, so we have the cameras in Speckle and Lucky Imaging as guiding and science cameras for all kinds of science goals. And also those cameras are used in adaptive optics. So one example is the Naomi project, which is the new adaptive optics module for interferometry, and that is at the VLTI in Chile. So that is just a basic overview. And now I would like to switch to our SCMOS cameras and just tell you what the benefits are when you compare it, for example, to CCD cameras. So the advantages of SCMOS detectors are that you can achieve low read noise, but at the same time, you can reach high frame rates. So you can go really fast, but still the read noise will be low. Then you have a high resolution and no charge transfer. And another good thing, like with the EMCCD, you have no mechanical shutter. And all of this is based on the sensor architecture of SCMOS. So we've also seen this image in Nick's presentation. But really, these advantages come from the fact that with a CCD, so you have light falling on the pixel, and then the charge is shifted from pixel to pixel until it is read out. But for an SCMOS, you have the photon falling on the pixel, and then the actual charge to voltage conversion takes place on the pixel level. So that's why you can go really, really fast. So if you summarize all of these characteristics, those cameras are really ideal if your application requires short exposures and high frame rates. So some examples are, for example, solar astronomy, or if you observe space debris or near-Earth objects, or even exoplanets, and it's suitable for adaptive optics. And here I just show you a brief overview of our large area CMOS cameras which are available. So you have here the model names, and I will focus on our Xyla and Neo cameras first. So you see they have all about the same sensor size, so about 2K by 2K. They have about the same pixel size, about the same quantum efficiency. They're all front illuminated. But you see here that the Neo cools further down, which obviously also affects our dark noise. But then we also see here, because the Xyla can be used with a camera link interface, you can go much faster with these 2 camera types. And if you just focus then in general on this row, you see that all of these SCMOS cameras offer really low read noise and high frame rates, which is shown in the row above. So yeah, so those, the Xyla and the Neo are 2K by 2K front illuminated cameras, which rather small pixel size. Then we have the Marana, also in different versions. So the Marana 4.2B-6 is actually a newer one. They're both back illuminated sensors, so also 2K by 2K. You see the pixel size here is more similar to our Xyla and Neo camera, but otherwise, as I said, it's back illuminated, so we have a high quantum efficiency, which you can also see here. And then we also have a deeper cooling of the sensor. It only offers rolling shutter though. And also, yeah, again, a really low read noise. And then one of our newest products as well is the large area Balor CMOS camera. That's a 4K by 4K device, so it's definitely significantly larger than our other cameras in CMOS for CMOS technology. So you have a 70 millimeter diagonal and a 12 micron pixel size. So this camera is also front illuminated. That's why you have 60% quantum efficiency, and it's also cooled down to about minus 30 degrees Celsius. And I also want to mention that so the Silas, those are backfilled cameras, but all of the other cameras, we have that the sensor is in a vacuum enclosure. So the sensor is protected and you don't have to repump the vacuum. So you really don't have to worry about that. So yeah, I gave you this overview, but now I would really like to focus on the Balor. So like I said, it's the largest CMOS device that we have, 4K by 4K. It offers 16.9 megapixel and has a really fast readout of 18.5 milliseconds. And at full frame, it offers 54 frames per second. So I would really recommend this camera for applications like space debris observations or large sky surveys because of its large sensor size, or even solar astronomy, exoplanet studies. And I just want to give you now the reasons why I think it's really suitable for these types of projects. So first of all, it is a shutter-free solution. It offers rolling and true global shutter. So true global shutter is really important for certain applications. So that's really a great feature to have. And like I mentioned on the slide before, the sensor of the Balor is in a permanent vacuum enclosure. So these 2 points really make the camera a low maintenance camera solution. And because the sensor is protected, that provides really exceptional sensor performance longevity. And these points are really important if, for example, your observatory is in very remote locations, which is very often the case for astronomy. Then, like you can see here, the camera offers really low read noise and fast readout. And if you compare the readout speed that you can achieve at full frame with a comparable size CCD, then you would see that the Balor can actually read out about 2,000 times faster than a CCD. So that is really impressive, I find. And another point that I would like to highlight is that the sensor is unique to Alnor. So the sensor can't be purchased anywhere else. It's just unique for our Balor camera. Then I have 3 more reasons I would like to share with you. Another reason that speaks for the Balor is that it has an option for an IRIC-B GPS timestamp. So that just means it offers you the possibility to sync your instrument across different instruments and sites. So that's really helpful. For example, if you do space debris tracking or asteroid tracking, some applications like that. Also, you can cool down to minus 30 degrees Celsius. And another important factor is that it offers a 100% duty cycle. So you can really take image after image and you don't lose the precious time. So first users of this camera are actually NASA JPL and the DAKIS Solar Telescope and another project in China. Good, so I talked about the benefits of the Balor, but I would also like to show you one of its first images. So you've probably seen this image on the right at the beginning of the year in the news. So that was actually taken in January 2020. It's from the Inouye Solar Telescope, and it really produced the highest resolution image of the solar surface which was ever taken. So that is really impressive. And so this image was taken with the First Light instrument, which was called the Visible Broadband Imager. And this imager really utilizes the Balor, and so the whole instrument is based in the telescope's rotating lab. So I found that is really impressive result, and I wanted to share that with you. Good, I'm at the end of my presentation, so that just gives you a brief summary of the different camera solutions that we offer for astronomy. So we have our Icon CCD series, which offers really low noise properties. It's suitable for long exposure times and offers a wide field of view because we have different sensor sizes up to 6K by 6K. and it's a back illuminated sensor, also with deep depletion. Then we have our EMCCD Ixon series, which offer, like I said in the beginning, they have also low noise properties, high sensitivity, you can achieve the high frame rates, and you have the frame transfer, so no mechanical shutter. And then our CMOS portfolio consisting of different front illuminated and back illuminated camera solutions, where you can also achieve or capture a large field of view at a high resolution and speed, while you still keep the noise levels down. And yeah, so those are all the benefits of these different camera technologies. And now, like Sean mentioned in the beginning, I have a little surprise for you. So I'll show that to you in a few seconds. So this is actually our second volume of our Andor comic. It's called Exoplanet Explorers, and it will be related to Nick's project. So yeah, if you want to hear more about when and how it's going to be released, then just check out our website and follow our social media channels, and you will hear more about that in the next weeks. So with that, I really thank you for your attention, and now we're open for questions.
Thanks very much, Ines. If you have any questions, please put them into the chat or the question tab, and we will answer them. I have a question here from Oliver. Ines, I think it's directed at you, and he just wants to know about the existing Andor CMOS cameras, what, you know, the Balor and so on. How are they, you know, which of them would you recommend for lucky imaging and speckle interferometry?
Well, it also depends on the field of view that he wants to achieve. So if he cares about a large sensor size or the pixel size, I mean, for lucky and speckle imaging, yeah, as of now, the most use is with our EMCCD cameras. But I would have to look into the details, which camera is most suitable from our CMOS portfolio for lucky and speckle imaging. It really depends on the project itself and the setup. And yeah, I would need to look into that. So he can feel free and send me an email and we can discuss that. Okay.
And Nick, I have a question here for you.
Yep.
Are the detectors on Gemini cooled, and how are they?
They're only using the onboard cooling that Andor has, the piezoelectric. So they cool down to -60, and that's just what we run them at. So there's no consumables.
Okay. Do you speckle the data on the fly at the telescope, or do you move them to a different facility for reconstruction? Do you speckle the data for the instruments users as a routine?
Currently, we do not. Currently, we have a data processing that happens after the fact. If there's a high priority target, we can do the reduction like that night, so that the reduction doesn't take that long. We've talked about implementing real-time reduction, but that may be a ways away. But that it's conceivable you could do real-time speckle reconstruction with clever computing and a lot of processing power. But usually we don't have that urgency, and we send it to IPAC and it's done there.
And how do you restore the extended objects that are many isoplanetic patches in extent? For example, Saturn.
Right.
This is a completely different problem to restoring close binary stars where you have isoplanetic fields of view.
Yeah, that's a pipeline that Elliot Horch has developed, and I am not sure of the intricacies of it, but the rough idea is I think that he does a patch at a time. So you're never getting the full reconstruction like we do with the stellar objects, because it is an extended object, and it's sort of a mosaic of looking at a section of it at a time and trying to reconstruct, or doing many different speckle reconstructions. So it's sort of a hybrid technique.
Thanks. This is another one. Is there any opportunity for doing short-term projects in speckle interferometry from home?
In this, you mean like operating currently? If the telescopes reopen, all of our instruments have been used remotely. I've run them from my apartment, so we're hoping that whenever the telescopes can open back up, we can get back on sky.
Okay.
Obviously, it's not ideal, but it's workable.
And what's the bandwidth of the Gemini Speckle instrument?
You mean the optical bandwidth?
Well, it just the questions you mentioned, switching between narrow and broadband. How narrow or how much broadband?
Narrow broadband filters. So it's standard Sloan filters for the broadband imaging if we want to do just traditional imaging, and then the Speckle filters are about 40 to 50 nanometer wide.
Okay, thanks.
And it's a trade-off. You can do Speckle in the broadband filters. What happens is you get bandwidth smearing, so it's harder to pick out the fringes. So the closer to monochromatic you are with interferometry, the easier it is to fit a sine curve to it, right?
Are there studies comparing EMCCDs and the CMOS performance in Speckle interferometry?
Not that I know of yet.
Okay.
But that is something we can maybe look into in the future. We can arrange a test of one of our CMOS cameras and send it to you, Nick, and you could maybe do some testing.
Yeah, no, it's conceivable to do.
And what phase retrieval methods are you using?
Sorry, what was that again?
What phase retrieval methods are you using exactly?
Phase retrieval methods. I can catch the word before retrieval method.
Phase?
I don't know. I'm still not hearing it.
I think maybe it's easier if we see that question written.
Yeah.
Is there a camera that has a faster frame rate, say of 50 kilohertz, but a smaller image?
Well, you can, with most of our cameras, you can select a region of interest, or even with the EMCCD, you can use a physical masking of the sensor to make the sensor size smaller and then have a higher frame rate. So that is possible. And actually these different regions and the resulting frame rates are shown in our spec sheets. There are always tables that show that.
I would make a recommendation. So ours are 1K by 1K. When we take data, typically we pick a region that fits all of the speckles, because you'll get artifacts if some of the speckles are chopped off. We'll read out at 256 by 256, but we do switch back to the 1K by 1K when the telescope slews to help with acquisition. And that's worked out really well to be efficient, because the telescope are real slim, slew, lock on, and then just bump it to the center, and then our software automatically picks a box around the centroid. So I'd be careful if designing a system that you account for that you've got to have some wiggle room.
Thanks for sharing that.
Yeah, if I can make a comment about the sizes, one of the things that our old cameras, we used to use the 897s, but probably they're 10 or 15 years ago when we first bought those. We went to 256 for two reasons. One is we only needed, for a star, we only needed a box that was a few arc seconds in size. But we also couldn't read out those 512 square full frame cameras fast enough back then. Mm-hmm. The new cameras we're using now, the new Andor EMCCDs, gave us two advantages. One is we still do 256 square, because why keep all the rest of the data for a point source that's outside the isoplanatic patch? So we have a data volume issue, just why carry it around for no reason. But because we can read the full frames out now at rates that are sort of what we call speckle rates, so 60 milliseconds, for example, which is not even challenging to them in most cases, we get lots of data very quickly. We can get hundreds and hundreds of gigabytes a night, so data becomes an issue just to move it around. But it's allowed us to go into these wider field speckle applications where we sort of stepwise across the whole field of view doing speckle reconstructions. And while we don't get the diffraction limit outside of about 1.5 arc seconds, we do beat the best native seeing by about a factor of 3 or more. So it won't reach the diffraction limit, but it might get you to images with the equivalent seeing of about 0.15 arc seconds. So it's pretty nice to have that larger field of view with the fast readout.
Okay, and just one final question: if we were to go towards 200 nanometer filters, are there any potential problems that might appear?
200 nanometer filter. I think you're going to have a loss of contrast at that. The narrower you are, the deeper in contrast I think you can go, because you're not smearing you're getting rid of the bandwidth smearing. You'd have to model that and check what your case is. It depends. There's a lot of factors, but I would, there's a trade-off because you're getting more light through, but I think you're going to run into the risk of bandwidth smearing. So you may want to have the option of narrower filters, but it really depends.
Yeah, there is a case of a person who does Speckle interferometry with Johnson filters. So Johnson filters are very wide, like Sloan filters. But there are two things that we've noticed about it: is they have a ADC in front of their instrument, so an atmospheric dispersion corrector, which we don't bother using, but they use it, and so they lose a little bit of light. But they also, we've noticed that their resolution isn't quite as good as what you might guess for the diffraction limit, because they lose a little resolution because of what Nick was just talking about, this bandwidth smearing. Or we've chosen to use narrowband filters without an ADC, and we never observe objects, well, I shouldn't say never, because some objects we have to, but we try never to observe objects that have an air mass greater than about 1.5.
Yeah, like if you were just going to be restricted to looking near the zenith, maybe 200 would work, but I'd have to calculate it.
Okay, brilliant, thanks. Okay, that's all the questions for today. Thanks very much to Nick and Steve for joining us, and thanks Enos as well.
Yeah, thanks.
You too.
Yeah, thank you guys.
Okay, thanks everyone.
Have a good day. Bye.
Bye.
Bye.